Welcome to this video on the extreme value theorem, which gives a fundamental property of continuous functions. So let's see what the statement says of this theorem. So let's take a function f defined on the interval ab with real values, and let's suppose that this function is continuous, be a continuous function. Then what do we have? Well, we have that this function has to have at least one maximum and one minimum. So then f attains one maximum and one minimum. Now, what does this mean? It means that there exist 2 points CD in the domain of my function f, so in the interval AB, such that f of c is less than or equal to f of x, and this is less than or equal to f of d, and this has to be true for all x in the domain of the function f in the interval AB. So what does this mean? It means that the values of my function f here are bounded by below by the value of f of c, which is a value attained by the function because it's f of c, a point in the domain, and they are bounded by above by f of d, which is another point attained, a value attained by the function. So let's try to understand why this theorem is true. So let's draw a simple continuous function. So let's draw first the real line here. Let's pick an a here, b here, and now we have to draw a continuous function from a to b. So it's very important that the values a, b are included here in the interval, which means that we start somewhere from f of a here and we end up somewhere else in b, f of b here. So now the game is just to draw a continuous function from a to b. Drawing a continuous function means that we must never lift our pen from the tablet. So let's do it. So you just have to start from a and go up to b. So let's see. Let's do anything here. Okay, we drew our continuous function, and now it's very clear what the situation is like. So we see that there is one maximum, and the maximum is here, and there is one minimum, and the minimum is there, and these values are obtained. So let's see. So we can draw on the x-axis. This gives the d point here. This was the maximum. This guy here, and here we've got c, the minimum, this guy here. So you see that f of x, the values of our function f of x, these guys here, are bounded by below by f of c, which is here, and by above by f of d, which is here. Good. So now let's go a little bit into the details and try to understand something more about the statement. So one thing is this existence here, and I would like to draw your attention to the fact that this is only existence and not uniqueness in general. So existence, not uniqueness. So this means that the maxima and minima may be more than one. So let's see why. Well, a very simple case one can take is a function like the sine. So if you take the sine of x and take, for example, the domain 0 for pi, so you do 2 periods of the sine, so what you get is the following. Start from 0, and then you go up and down, right, twice. This is 4 pi, this was 2 pi. So you see that this function has 2 maxima here, and 2 minima here and here. So in general, we may not have uniqueness of the minima and the maxima. Good. The other thing about the statement is the fact that the interval, that the function has to be continuous. So why is this crucial? Well, if the function is not continuous, the statement may not hold. So let's see why. What if f is not continuous? So in this case, let's draw as usual our interval AB. So let's do something like this. So far the function was continuous, but now here I decide to do a jump, So let's suppose the value in this point is here, and then I start from here again, and I go up in B. So you see that this function doesn't have a minimum and doesn't have a maximum. Why? Well, if you look at it, you see that the maxima of these functions are achieved near this point, but the point here is not attained, because being the function not continuous, I am allowed to define the function in this point in another point here. So the maximum is not attained, and the same applies to the minimum. The minimum values of the function are here, but the minimum is not attained. So you see why continuity is an essential assumption of this theorem. So now let's go back to the statement and let's look at the interval here. So why, for example, the interval has to be closed? So let's see why. Let's see what happens if the interval is not closed. So what if the interval is not closed? Well, also in this case, it's not difficult to draw a function which doesn't satisfy the statement of the theorem. Let's take 1 over x, and let's take x in 0, 1. Well, the graph of this function is the following. So 1 is excluded here. So the function is continuous, of course, but since the extrema of the interval are not included here and here, in 0 I'm allowed to go up to plus infinity, so there is no maximum. Actually, the function is not bounded. And in 1 I'm allowed not to attain the minimum value here, because the interval is open. And so the function doesn't have a minimum either. So last thing I want to mention is why it is important that the interval is bounded. So why AB, and we cannot take plus or minus infinity. So what if the interval is unbounded? And well, again, as above, also in this case, the statement doesn't hold, and we can consider a very simple case. You just need f of x equals x. You take x in R. This function is continuous. The domain of f is a closed interval, but it's not bounded. And indeed, f of x, the graph of f of x, is this one. And you clearly see that there is no maximum because the function goes up to plus infinity, and there is no minimum because it goes down to minus infinity. Thank you for listening.